last time we introduced the topic of stoichiometry, and in order to make that process work, you've got to write your compounds correctly and put them in a chemical reaction statement, which is like sentences. The alphabet is symbols, words are the compounds, and sentences are the reaction. But we were focused primarily on reactions that had solid or gas, actually liquid, any of those pure phases would work the way we did it. Now we're going to get into types of chemical reactions and then introduce the topic of stoichiometry and solutions. A lot of chemical reactions occur in solution, and we're going to limit ourselves to aqueous solutions, right? Where whatever we put into the reaction is dissolved in water. Okay, since we're going to put everything in water, we need to understand a little bit about water. Now, we might be jumping the gun a little bit because later on we introduce topics that allow us to actually prove to ourselves that that is the shape of the water molecule. It has one oxygen. We know that water is this. Right? That's its molecular formula. But its shape is like this. And what that determines for the water molecule is its polarity. You understand? What we mean by polarity is it's kind of like a magnet. It has north and south poles. North poles of two magnets repel, north and south attract. Well, polarity in a molecule has to do with slight or incomplete charges. That's why we use that little delta. Delta just means partial. Partial charge, and up here we have partial negative charge. And because this molecule is bent, if it were straight and we had the positives here and negative in the middle, then they would cancel one another. And the molecule would be nonpolar. It would not have no net partial charge. But since it's bent like this, then more of the positive is on this side, more of the negatives on that side. There he is. We say it's polar negative toward the oxygen, which simply means that in pure water, these molecules will orient themselves so that this negative side is close to that positive side. And that partial bonding gives water its physical characteristics. In other words, if it were not for this, if water were a nonpolar molecule and it followed the same trend as its neighbors, the dihydrides of sulfur and selenium and tellurium, its boiling point would be in the negative Celsius. Right? There would be no liquid water on the surface of the earth. It'd all be gas. But this strength of attraction allows it to condense into a liquid at room temperature, and it has a much higher boiling point. That's one of the physical characteristics that this facilitates. The other is that if this is going to be the major component in a solution, and we'll define it in a minute, it's called a solvent, then anything we put into it, if the minor components we put into it are also polar, then they will orient themselves so that their positive side is oriented here and their negative side is oriented there. And you stand a much better chance of putting that minor component into solution. So it's all based upon the polarity of the molecule. We'll go into a lot more detail on polarity when we get to bonds and shapes of molecules. But this is enough for now. Okay, we've got a little video here. Let's see. Oh, there's no narration. Right. It's probably a good thing this is a French-Canadian production. They probably wouldn't speak our language anyway. So that's a representation of the water molecule with its oxygen on the negative side and the two hydrogens on the other side. And what we're going to try to do is put sodium chloride in solution. And this is what happens. There's the sodium chloride crystal. Sodium's the red, chlorides are the blues. See how they orient themselves, positive to negative, negative, positive. And they pull the ions out of the crystal and surround it. We call that hydration. And that keeps them in solution. We'll talk a little more about that. I think we get into those kind of details in the second semester. Right, so this is enough for now. And they'll keep doing that until one of two conditions are met. Either all of the sodium chloride solid is now in solution, or there's so much in solution that it can't hold anymore. And then it'll stop dissolving. We'll still have some solid in the bottom. All right. So some definitions. I mentioned solvent before. Solvent in any solution is the major component. In our case, we're going to use water. Liquid water is our solvent. And you can only have one solvent. Major, one. The minors are the solutes. They're minor components. And you can have many if you need them, one or many. Now, I'll get to the last one in a minute. This is true for the vast majority of solutions. Once the solution is made, and even if you reach the point where it can't hold anymore, these are still minor components, and most of it is the solvent. But there are some exceptions. One notable one is sucrose, table sugar in water. You can put more table sugar into solution than you have water left, and it's still a solution. I mean, you ever make hummingbird feeder juice, right? Usually half and half. You can keep going. You can put more sugar in there than just a cup to a cup of water, and it'll go right into solution until you exceed the solute exceeds the amount of solvent. But we still consider the solvent water, because usually you start off with a lot of water and you put sugar into it. So where we started from was the major was water and the minor was sugar. Now there are two types of compounds that can go into solution, right? The molecular compounds, where you have the molecule, it behaves as a single unit. Water is a good example of that, but it's our solvent, so we got to go somewhere else. Sugar molecules, they are true molecules. They exist as a single unit, and I won't draw the structure, but their formula is H2O11, I think. Or is it 24? I think it's 24. Anyway, it's a pretty big molecule, and it goes into solution without dissociating. It doesn't break apart. It's the whole molecule in solution. And it has no charge. It has partial charges all over it. It's got a lot of these hydroxyl groups on it, right? So you get this uneven distribution of charge toward the negative here and the positive here. And that interacts with water, the rest of the molecule over here, right? But it's got lots of these on it. So they interact with water molecules just like water molecules interact with each other, right? Positive, negative, positive, negative. So you can put a lot of sugar in solution because it has a whole bunch of these on each molecule. But the point is, the molecule doesn't break apart. It is still a molecule in solution. The other type of solute is ionic, right? Like sodium chloride. we just saw in that film. It's made up of these ions in a matrix as a solid, crystal matrix of 1-to-1 ratio, and it can be any size. This is the simplest whole number ratio of sodiums to chlorines, right? It's simpler to write that rather than write a subscript of 342 million. We just say the simplest ratio. That's the way ionic solids are. And when they go into solution, if they go into solution, then they break apart. And when they do that, now we can call them electrolytes. Electrolyte is simply an operationally defined term for any substance that can be put into solution, and now the solution will conduct electricity. Right? Sodium chloride solid, like that, if you put an electrode on either side like this, right, like that, like a battery, and then you hook it up to a light bulb, right, like that, you get nothing. Right? The circuit is not completed because these ions are locked in place. They cannot move. So there's no conduction of current across the crystal. So solid sodium chloride is an insulator, electrical insulator. But if you melt it or you put it in solution, now these ions are free to move. So you can get the chlorides moving one direction, the sodium's moving the other direction depending on the poles. And it will conduct electricity, and you get the evidence of that conduction with your light. Those are electrolytes. When you get a blood or a urine sample analysis back from the lab, the doctor sees a list, and these are all these electrolytes. They'll have sodium and chlorine and calcium and magnesium, potassium, and some others, carbonates. These are all electrolytes. They're ions in solution or in your plasma, blood plasma, or in your urine, whichever the case may be. And the balanced, they have normal ranges, of course, and the computers now will tell them it's out of range or it's in range, and then it simplifies the doctor's diagnosis. But they're looking for those electrolytes. I think, what do they call it? I don't know what the terminology is. Complete blood panel or something like that.
CBC.
CBD?
CBC.
CBC.
Yeah,
Okay.
Complete blood count.
Okay, well that gives you also, that's for the reds and whites, right? There's another one that is just a simple abbreviation, and it gives you this whole list of stuff.
I'll look at
it. Yeah, that's the problem with acronyms. I mean, after a while, you associate the acronym with the analysis, and what the acronym means doesn't matter anymore. Okay, so if the substance that we put in solution, the solute, completely dissociates, like sodium chloride, potassium chloride, or even an acid like vinegar or hydrochloric acid, if you put that in there and it breaks apart into ions completely, then it'll be a very, very good conductor of electricity. We call those strong electrolytes. Weak electrolytes are only partially dissociated. Like, let's see. Remember that one? Polyatomic ion, acetate. It's an acid, acetic acid. It only partially breaks apart. When it goes into solution, just like that, but only some of it, very small amount, breaks apart into hydrogen ions and acetate ions. Okay? In solution. So it doesn't conduct electricity very well. That's a weak electrolyte. And then sugar is our non-electrolyte. It will not conduct electricity because it's not ionic. Let's see. Got another video. Let's see what it has to say.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
There we go.
The sugar is non-aqueous?
It's non-electrolyte.
No.
Right. It does go into solution in huge amounts, but it doesn't dissociate into ions, so it will not conduct electricity. So when we're discussing chemical reactions of solutions, we need to know something about the nature of the reaction, the various physical attributes, right? What type of solution is it? How concentrated are the chemicals? And we need a way to quantify those values, those concentrations. So one of the most common ways is called molarity. Molarity, we abbreviate with a big M. Is simply the ratio of moles, and I use an N with no zero. If I put a zero up there, that's a neutron. But if I don't put a zero up there, that's moles. Right? That's moles. Moles of the solute in a certain amount of volume, liters of solution. Okay, that's the definition of molarity. The value of this formula, like any equation, is that if we know two of these, since there are three variables, if we know the values for two of them, we can solve for the third one. Right? It's just algebra. But we have to be sure and use the right units of measure. Okay. And it's also important that this is the volume of the solution after the solute goes into solution. We have to set this volume when we're making the solution after it goes into solution, because several things can happen. One is the solution could be exothermic or endothermic. It could get hot or it could get cold, and that will affect the volume. Okay, so we have to make the final adjustment once the solution has come to room temperature. The other is a good thing. Since we know this ratio, then if we know we need a certain number of moles, then we can solve it for moles. And that would simply be molarity times volume. That makes it a very straightforward, simple way to assess the concentration or obtain the right number of moles for a reaction that we propose. If, on the other hand, we know that we need a certain number of moles out of this one, then we can just, let's use a capital. We can just move this one over here like this. And, well, that puts 1 over volume. Okay, so I'm going to have to invert it. Volume equals moles over molarity. So if we need, how much volume do I need from this molarity solution to give me that number of moles? Okay, so then I take that volume out of the stock, and I know I possess now, with that volume, I know I have exactly that many moles. Okay, when we calculate it, right, we just need to know the moles, in this case, of hydrogen chloride, and the final volume. Okay, and how do we assure that? Well, we have volumetric glassware that is calibrated to contain a certain volume. So, and most of them look like this. They have a long neck, and then they have this big bulb at the bottom. And then there's a mark. It's either painted on, usually it's scratched on, so you can't lose it. And that, let's just say for this one, that's 1 liter. Okay, we know that at room temperature, and it will have scribed or painted on the neck the temperature at which it was calibrated. Usually it's 20 degrees. But 20 and 25 are so close together, usually for our purposes, it doesn't matter that much. It's when they're really far apart, like 50 degrees or 60 degrees, or it goes down to 10 degrees. When you make the solution, then it has an effect on the calibration volume. So you would put the mass in here, right? Because we don't have any instruments that will measure in moles, right? They only measure in mass. So if you know you need this many moles, you've got to consider the compound that's your solute and its molar mass, and then convert that number of moles into mass so that you can measure out the mass to put into. Okay? That's an extra step. Now, once you got it down here, this solid, say, then you start, well, actually, it's better if you put some liquid in there to begin with, like this. And then you start adding water, and you get up to maybe right in here somewhere. And then maybe you'll either have a thermometer in it or you feel it and say, is it hot or cold? If it's measurably colder or hotter, then you want to wait until it comes to room temperature. Okay, and you want to be sure all of this is in solution too. Right, mix it up real good. Once that happens, then you can finish adding the solvent, water, to bring it to this mark. And all glassware is calibrated for a concave meniscus. That is, let's blow it up. If this is the neck and you have that mark, then you fill up the solution until it goes like that. The bottom of the meniscus is the calibration point. Okay. All right, and once you're at room temperature and you filled it up that mark and you mix it up real good, right, you may have either parafilm or it may have a glass stopper. Then you mix it up real good. And you have a solution that is a known molarity. Let's see, what other cautions? Well, if it's an exothermic reaction and you filled it up to the mark right here, then as it cools, it's going to come down to here, right? It's going to be less. Those are not problems. The exothermic reactions, if you're not too far off, they can be made up volume. But if it's an endothermic, if it gets cold and you have it here, then when it warms up, you're going to be up there and you're screwed. Right? You have to start all over again. So that's molarity. And here's an example. If we're told we have 500-gram sample of potassium phosphate, dissolve it in water to make up 1.5 liters of solution, and I can't for the life of me, I've never seen a 1.5 liter volumetric glassware. So we're just taking it at face value. So we're given 500 grams of what? Potassium phosphate. This is where you have to know how to write the compound. Otherwise, you can't calculate the molar mass and do the rest of the problem. So potassium and phosphate. Phosphate is a polyatomic ion with a 3- charge, and potassium is an alkali metal with a +1 charge. So to balance them, you need 3 of those, right? 3 positives to balance the 3 negatives. Now that we have the formula, we can calculate its molar mass. Right. I'll spend time on this one, but subsequent ones we might have to breeze through them. So potassium, we'll look up potassium. It's 39.10 to 2 decimal places. 39.10 times 3. Then phosphorus is 3097 grams per mole. And oxygen, we have 4 of those. And there's 16 each. Okay, so we add those up 3 times, and then 30.97 times 1, and then 16, there's 64 for oxygen. So that's 125.94 grams per mole. That way, we can convert this 500 grams. Let's see, I need to put it over here. Oops. Decimal's in the wrong place. We need to convert that to moles. So grams on the bottom, moles on the top, right? We'll cancel the grams. That means this 125 goes on the bottom. And we actually divide it into that value. And I get 3.97 moles of potassium phosphate. Now, does that look reasonable? Let's see. 2 times that would be about 250. And 2 times that would be 4 times would be, yeah, that's about right. Okay, that's the number of moles. And the volume, we have everything we need now. 3.97 moles per 1.5 liter final volume. Right. We can't just say, we added this to a 1.5 liter volume of water, because what happens is sometimes the solute goes into holes and it doesn't change the volume. So if you know the volume of this and you know the volume of your water, it doesn't follow that the final volume is addition of those two. Because once you put them in solution, you could get a completely different volume out of it. That's why we go to the final volume here. We need some way to volumetrically fix and accurately fix that final volume. So, has anybody done that calculation? What is it? 2 point something, isn't it?
2.6.
2 point, oops, sorry. Let's see, we got 3 significant figures.
2.60.
Okay. That's molarity. Now that we know the molarity of that solution, we can use the formula and take, say, I don't know, 20 milliliters out of it and say, and calculate how many moles of potassium phosphate we have. Let's see, did I do that right? Uh-oh. I miscalculated that apparently. Okay, hold on a second. Let me see what I did wrong. 39.10, 3 times that, and 30.97, and 64. Oop, I did make a mistake. Nobody caught me. 212.27. Okay, this is going to change everything. That was right with the wrong numbers. 212.27, which is what? A little over 2, isn't it? Well, 2.355. 2.355 moles. So 2.355 moles. Now we can divide and get a value, which should be, in the interest of time, I'll just pop up the answer there. 1.57 molar. Okay. All right, let's see. Okay. So that's the molarity of the compound. But suppose you're in the medical profession and you're trying not to kill your patients. So you want your solution to be isotonic with the patient's plasma, with the fluids, right? If you calculate based solely on the concentration of the compound, you're going to be way too high because it breaks apart, and the osmotic pressure from that solution will be, in that case, 4 times as high as you think it is, right? Because it breaks up into 3 potassiums and 1 phosphate. So we have to be careful, and that's what this slide is about. We want to know the concentration of the ions in order to keep from killing the patient. Right? In this case, 0.25 molar calcium chloride is actually 0.25 molar calcium and 0.5 molar chloride. We doubled the number of particles of chloride by the dissociation. Okay? So the total concentration of ions in this sample is 0.75 molar. Okay? What's isotonic with our system? Let's say sodium chloride, 0.9 mass percent, mass volume percent. Sodium chloride is pretty close to isotonic. Okay. The problem with that is it floods your patient's system with sodium and chloride ions. Now, if they're bleeding out and you don't know what their blood type is and you want to keep their fluid up, then yeah, you make that choice. If you're on the way to the hospital in an EM situation, or if you know your patient is not diabetic, you can use D5W. Dextrose 5% by weight is pretty close to isotonic. But if they've got one of those diabetic bracelets on, you don't want to give them this. They might be in a diabetic coma by the time you get to the hospital. So that's why very often what you'll see in the hospital is what they call lactated ringers. It's a mixture of various non-electrolytes and electrolytes to give you an isotonic solution, but with less of an impact that either one of these would have had. Okay. You might have lactated ringers dripping, and then you'll have on the side, you'll have another bag of maybe antibiotic or some other chemical they want to add to it. As long as it doesn't affect the tonicity of the ringers, then you're good to go. Okay. So how about which of the following solutions contains the greatest number of ions? I'm going to run out of time if I keep doing this. What we need to understand is this formula equals moles per unit volume. And if we're looking for number of ions, we're looking for that one right there. So if we solve for that one, moles equals molarity times volume. If we're directly comparing, we're trying to compare these 4 solutions, then we need to consider 2 things based on the question. Which one has the greatest number of ions? Read it backwards. Which one has ions? Only A, B, and C. D doesn't have ions. So we don't have to waste our time with D. That's sucrose. The others, if we have 400 milliliters of 0.1 molar sodium chloride, 0.1 molar sodium chloride, let's put the rest of them up there. Same concentration, molar of calcium chloride, and iron 3 chloride with 1 molar. Now, why did I say iron trichloride? Why did I just say iron chloride? Because it's a
There's
type,
3.
it's a type 2 compound. We have to know what the charge is in order to name a type 2. This is an alkaline earth. That's an alkali metal. They have fixed charges, so we don't have to say what the charge is. But this one, we do have to say what the charge is. Oh, I've used the wrong one today. 3. So this would have a 3+ charge for naming the compound. Okay, so we have so many milliliters. This is the molarity. Now we need the volume. The volume has to be in units of liters, correct? So how many liters is 400 milliliters? If it takes 1,000 milliliters to make a liter, that's 4/10, isn't it? 0.4 liters. Yeah. So if we do that, 0.4 liters, and then 0.3 liters, and then 0.2 liters. Okay, that gives us the number of moles of the compound. But the question is ions. Right. So if this is moles of compound, we need to convert moles of compound to moles of ions. And same thing for each one of them. So what's the ratio? Well, for every mole of compound here, we have 2 ions, don't we? Okay. And the reason I put this on the bottom is because that's 1 unit of this. And this is 2 units of ions. This ratio would be 2 and 1 is 3. This would be 4 and 1. Okay. So that's the thinking part. The rest is number crunching. So we would say 0.1 times 0.4 times 2. And that's 8 times 10 to the minus 2 moles of ions. Then 0.1 times 0.3 times 3 is 9 times 10 to the minus 2 moles of ions. And the last one is 0.1 times 0.2 times 4. And that's 8 times 10 to the minus 2 moles of ions. So the one with the greatest number out of this selection is that one. Okay. We had to go through the process of calculating them in order to answer the question because we can't tell from just this. We need to know also that and that to answer the question.
How you probably already said this, but
Okay.
like for example with the iron chloride, when it's a type 2, how do you know that the transition metal, like there's not 3 irons with a +1 charge to match the 3 chlorides instead of just 1 iron with a +3 charge?
Well, the way the formula is written, we know that all halogens are a -1 charge.
Right.
Yeah. So that means that we have a total of 3 minuses here on this side of on the anion side of the equation or the formula. So if we've only got 1 iron, that 1 iron has to balance these 3 minuses.
Okay, never mind. I understand.
Yeah. Okay.
Yeah.
Okay, so let's see. There it is. So again, I think we went through this last time. What's the question? How do you get there? And then does it make sense? That's your series of procedures.
Can you hear me?
Yes.
Oh, sorry. I was wondering, when did we cover chapter 3? Did we have class Tuesday afternoon?
Yeah.
Oh, okay. I didn't realize. I thought you said the day of the exam there is no class. I think I misunderstood that.
Oh, no, there's no lab.
Oh, so the class is during the lab session instead.
Correct.
Okay, I was so confused why we were not covering chapter 3, but I'll go back and watch that. Thank you.
Yeah, I've posted the video. It's up and running now.
Perfect. Thank you so much.
Okay. All right. Now that we know this definition for molarity, we're going to go into a practical scenario, and I'll describe a situation from my past. I used to work in a soil testing lab, and we would analyze hundreds of samples a day usually by some extraction. We would extract with a liquid solution of various salts and maybe acids, and it would extract elements from the soil, and we filter them and then run them through our either plasma spectrometer or an atomic absorption spectrometer and quantify the elements so that we could tell the farmer, you've got this much in your soil, you're good to go, or you don't have enough, you need to supplement it, things like that. So when we made up the extractants, they were relatively dilute solutions. Right? If we made them up every day, it would take us an hour, 2 hours in the morning just to make those things up. Because you got to wait for them to go into solution. You got to let them come to room temperature, finish them off. So what we did was we'd make, in the same ratio of solutes to solvent, we would make them up concentrated. The ratio is fixed. So we just boost their concentration by a factor of 10 or 100 and make a concentrated stock solution. And that way, all we'd have to do is come in, take a known amount and dilute it up to a known volume, and then we had our extracting solution. We knew the concentrations were correct and we'd go on. So here's how that works. If you have a stock solution here in this container, and say this is the molarity of the concentrated one, or in this case, M1. That's the molarity of the concentrated. We know the concentration of, say, let's keep it simple, one solute is this concentration. And we want to dilute it to a known volume, so we use our volumetric glassware. There. And we know we want this diluted concentration over here. Okay? So we would take out an aliquot, a known volume of this one. We'd take a volume out of that one, a volume of the concentrated one, and we put it in here. Right? And the volume of this total now would be the diluted volume. Okay? All right. So, what's the same in all this, in this picture? What does not change? If we multiply this one times that one, what do we get? We get the moles transferred, right? If molarity equals moles per unit volume, then moles equals molarity times volume. So M times V gives us the number of moles that we're transferring. Okay? How many end up over here? Those two are exactly equal. Right? We didn't create or destroy anything when we moved it. Okay, so if on this side, we can say molarity dilute times molarity volume dilute, that's equal to in the diluted number of moles. Well, what is it in math? I forget the name of the rule. If A equals B and B equals C, then A equals C. Is that commutative property? I think. You never heard that before? Okay, don't remember the name of it. That's what we've got going here. This equals to that, and that equals to that, but this equals that. So these two are equal. Right? This one is equal to that one. Or as I put it there, M1V1 equals M2V2. That's why this works. All we have to do is take this concentrated solution, pull out the right number of the right volume, put it in that one, dilute it to this volume, and then we know that we have that concentration.
So when you transfer from the concentrated one
Uh-huh.
over to there,
Uh-huh.
you're not taking all of that solution?
No. Just an aliquot.
Okay.
Yeah, just a known volume. This is the volume we're pulling out of that concentrated one.
And so it's like,
It could be any volume down here, but the volume we pull out of here is a small part of that.
then when it gets into the diluter.
Then we put it, then we add more solvent.
Okay. Then
Yeah.
there's less of.
Right, so the concentration goes down. But it goes down to a known amount because we have that formula to work with.
And then that formula means there's still the same amount of moles per like.
Well, there's the same amount of moles transferred, but the concentration is less over here
Okay.
because you have more solvent. Yeah, we just fill it up with more solvent, water, usually. That way, we don't have to spend all our time in the morning making up a fresh dilute solution. We got this one usually in a big tank, glass bottle usually, so that we don't contaminate it. And then we just draw off that bottle for a couple of months. And then when we need it, we spend enough time to make up a concentrated solution. Okay, so this is the animated version of why it works. There we go. And there it is. Okay. I'm gonna skip this. This basically says which one of these would lead to a decrease in the concentration of the salt in solution, sodium chloride. If you add water, oh yeah, that would decrease the concentration. Pour some of the solution down the drain. Because you're pouring a proportional amount of solvent and solute at the same time. So you got the same concentration left over. Add more sodium chloride. No, that would increase the concentration. Let the solution sit out in the open air for a couple of days. No, sodium chloride is not volatile, water is. So water would evaporate and increase the concentration of your solute. At least two of the above? No, just that one. Okay. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? Okay, when you have a problem like this, or like any problem, I think it's useful to first, what's the question? And then what information are you given? What is the minimum volume of 2 molar sodium hydroxide? And we're going from 2 molar to 0.8 molar. So the concentrated volume, concentrated molarity is 2 molar, correct? And the diluted concentration is 0.800 molar. So I extract information from the problem because word problems are designed to confuse. Yeah. So we pull that information out and we say, okay, solution needed to make 150 milliliters. So what is that? Is that the volume you pull out of this, or is that the final volume?
That's the final.
Yeah. So this would be, the diluted volume would be 150 milliliters. Okay. So the question is, what volume do we pull out of the concentrated one? Now we can set up our equation and be confident that we put the numbers in the right place. If you try to work the problem straight from here to paper, then you're liable to put those numbers in the wrong place and obviously get the wrong answer. So if our equation is this, concentrated, dilute, then we want to solve for this one. There we go. Now we can plug our numbers in. And one thing you'll notice is these are ratios to one another. So when you have this situation, you don't have to change that to liters. If you use this volume in the VD, you're going to get those units in the VC. Okay, so all we have to do is put, let's see, what is it? 0.800 molar, and volume of dilute is 150 milliliters over concentrated 2. Notice that these cancel and we're left with milliliters, which is what we want. Okay. So let's see, 2 into that 75 and 0.8 times 75. I'm sorry, I can't do that with my head. Times 75. I get 60. 60.03 significant figures. And this is milliliters. So what that says is, if we take 60 milliliters of this one and dilute it to 150 milliliters with solvent, we will get that concentration. Let's see, did I animate that one or just put the answer up? I did animate it. There we go. Okay. If you do it enough, it becomes second nature. In fact, a lot of these you can do in your head. When I make up standards for my argon plasma instrument, I could do them in my head. Just write down the values and then mix them up. If you do it often enough, that's just the nature. Right? Okay. And that just emphasizes the point. Since this is a ratio, we don't have to change the volume. The volume we put in is the volume unit we get out. We could change it to liters, sure, but the answer would be in liters. And most volumetric devices in the lab are measured in milliliters. Okay, now let's talk about types of reactions. These are defined by some particular defining characteristic of the reaction. So precipitation reactions say that when you put two solutions together and they're clear, there's nothing in there but the solution, you can see right through them. When you put those two together, the combination of the solutes reacts and produces a solid that precipitates out of solution. Right? It may be very finely divided. It may take a while for it to settle, but you did produce a solid. One of the ways to tell is shine a light through it. Right? In a solution, if you shine a light through the solution, let's see, here's our flashlight. If you shine a light through a solution, it'll come out the other side and you can see it. But from this side, from right angles, you won't see a thing. That light goes through the solution and you can't see it. It doesn't leave a trace or a path. But if you have particles in there, they will diffuse the light and reflect it, and you can see the beam going through. Okay. That's called the Tyndall effect. So that's one way we can use to indicate that a precipitate has formed. The solid that comes out of that reaction is called a precipitate, often abbreviated PPT. Acid-base reactions. Simple. Put an acid together and a base together and they react. Oxidation reduction reactions is a little harder to explain. They always require a transfer of electrons from one atom to the next, usually from between reactants. Those are major types. Then we have other types of reactions based upon what they do. And it's important to recognize that one of these major types may also be one of the other types. You can have multiple types assigned to a reaction. Combination reaction, where you put a simple, like an element to an element, and make a compound. That's a synthesis or combination. Or a decomposition, where you take that compound and you break it apart into the elements. Single displacement. I think I've got slides on these, so I'm just going to name them. Single displacement is where you have an element replacing one of the elements in a compound. So it's an element on this side, it's in the compound on the other. So that means that the compound, the element that was replaced, ends up as an element on the other side. Double displacement, you have a binary compound, and they swap partners. Cation swap places. And a combustion reaction is a special kind. You always have oxygen as a reactant, and it's always an oxidation reduction reaction also. So let's look at the slides. Precipitation reaction is also a double displacement reaction. For instance, if I have silver nitrate in solution, and I react it with, say, potassium chloride in solution, then this is a double displacement. These cations will swap places. Okay, so the potassium and the nitrate on this side, and then the silver and the chloride combine. Okay, but the silver and the chloride are insoluble. When they form that compound, they drop out as a precipitate. That's a double displacement and a precipitation reaction. Now, why do they do that? Well, this is the molecular equivalent, or the formula equation. But what actually happens in solution is these guys break apart. Right? That's actually what you have in solution. You have the ions in solution. And this, before you put them together, this is a solution of sodium, silver ions, and nitrate ions. And this is a solution of potassium ions and chloride ions. Okay, separate solutions until you put them together and mix them. Now the ions can interact with the cations can interact with these anions, and this cation can interact with those anions, and that's where you get the reaction. Now these, they're still in ionic form. This is still potassium and nitrate in solution, but this one, the interaction of that cation and that anion makes a solid. Okay. So that double displacement is also a precipitation reaction. Here's another example. Barium nitrate. On the left hand, let's see, we got barium. I'm not sure which one of those big spheres is barium.
It's the like the purplish one.
Purplish one, okay. Oh yeah. There's the legend on the side. Just look at it, right? So we got the barium ions, we got the potassium ions, we got the nitrate ions, and we got the chromate ions, and they're all mixed together. And then what happens for the reaction is you get potassium and the nitrate are still in solution, right? The reds, right? The red and the blue reds, those are still in solution because they don't form a precipitate. They don't make a solid. They stay in solution. What's left over is the barium and the chromate ion. They get together and form that yellow precipitate. So there's another double displacement reaction that forms a precipitate. Okay? And the reaction is balanced up there. And since we have polyatomic ions that don't change in the process, then it's easy to balance this equation because you got nitrate on both sides. We can use that as a balancing unit. And we got chromate on both sides. We can use that as a balancing unit. Let's see. I think this is pretty. They use sodium chloride instead of potassium chloride. There you go. There's your precipitate. Forms almost instantly. All right, now let's go to the next one. Oops, I went too far. More types of precipitates. That's the one we were just looking at. Magnified. This one is sodium thiosulfate. So the thiosulfate is a polyatomic ion, and it interacts with silver to make a precipitate also. Here we've got barium and sulfate. Anybody ever had a barium enema or an X-ray? That's what they use, barium sulfate. They use it because it's insoluble, but it attenuates X-rays very well. So they load you up in the bottom end with barium sulfate solution, and that way you can see all the details of your colon. Here we have a very complex precipitate. But it's pretty. All right. So let's go here. All right. I'm gonna leave that up there just in case I need it again. The AQ means aqueous solution. S we put on there if it's a solid. And this can either be a solid as a reactant. In our case, it's a solid as a product. And then L would be liquid. Right? If water were one of our reactants at room temperature, we'd put an L there for liquid water. And then gases, you can have gases react also. For now, we're going to say it's either soluble or insoluble. But the truth of the matter is it's on a continuum. Right? Even silver chloride in solution, there's some silver ion and some chloride ion still in solution. Not all of it forms, but most of it, 99.999% of it is the solid silver chloride. But there's some in solution, and we're going to learn how to calculate the how much is left in solution. I'm not sure. We're going to do that this semester. Where's that for next semester? Let's see. I think it's next semester. Yeah, second semester we do that. So no need to panic. These are solubility rules. If you were in a chemistry class that was prerequisite for a chemistry degree, you'd memorize these rules. But since that's not our purpose, I don't think anybody in here wants a chemistry degree, right? You're doing something else. So these are the rules that were used to construct, hold on, construct, where is it? There it is. Construct that table. That table is in your review document in the back, which means on the exam, it'll also be there. You just need to learn how to use it, right? We have cations across the top, anions down the left-hand side, and you just follow them until they meet in the square. And if it's gray, they form a precipitate. If it's clear, they don't. They stay in solution. Okay. All right, so let's go back. Let's see, where was I? Here we go. Oops. Which of the following ions forms compounds with lead 2 plus that are generally soluble in water? Go to that chart and you take the lead 2 plus across the top, find where it is, drop down until you reach the cross for each of them: sulfide, chloride, nitrate, sulfate. And we find that the only one that's soluble, and then you got the ringer down there that's sodium ions. You don't form compounds with 2 cations, right? Throw that one out. Nitrate. One of the rules, the first rule actually, all nitrates are soluble without exception. If you have a nitrate compound, that's why we use silver nitrate, because it's soluble before we put them together. All nitrates are soluble. Lead to chloride, lead to sulfide, lead to sulfate, they're all insoluble. They form precipitates in solution. Now, I knew I was going to need this. Okay, so they use sodium chloride. I'm going to stick with potassium chloride. This is the formula equation, or sometimes we call it, man, that didn't last long. The formula or molecular equation. I hesitate to call it molecular because these aren't molecules. But the formula equation gives you everything in condensed form so that we can balance the equation. That's its main purpose. This compound goes into solution, that one in solution, it produces this one and that one. That way we can balance the equation. And the equation should be balanced as written. Yes, that's balanced. This is the complete ionic equation. That is, we come face to face with reality. Ions are actually in solution. That's where the reaction happens. And then we produce this to be complete, aqueous, and then silver chloride solid. So this equation is the complete ionic equation. All right. Now, what do you notice about this equation? That's the same. See, that's the same on both sides. Potassium's the same on both sides. It didn't do anything. Nitrate's the same on both sides. It didn't do anything either. So if we use a mathematical rule and cancel this one on that side and this one on that side, what do you got left? You got silver ions plus chloride ions yield silver chloride solid. This is the net ionic equation. That's where the business happens right there. The advantage to looking at it this way is if I don't have potassium chloride in my lab, then I can use sodium chloride and get the same reaction. As long as I account for the right molar mass and calculate the correct moles to add, right? It does require that extra effort. But still, this is the net ionic equation for both of them. So if you have to substitute a reagent, as long as one of the cation or anion is spectator, that's what we call these. These are spectators. As long as they're spectators, then it doesn't matter.
Are they spectators because they're soluble?
No,
Or why
it's
are
because
they-
they're the same on both sides. They don't contribute to the reaction. The reaction is actually the precipitation. So we separate the ions because that's what really happens in solution. These are spectators because, notice, they're the same on both sides.
So why in this reaction couldn't like well never mind. Yeah.
Now, sometimes that's what it takes.
Yeah.
Start to ask a question and then your mind figures it out.
Yeah.
Okay, so there's the net ionic equation for this reaction. And the sodium, or in our case, the potassium and the nitrate are spectators. They just sit there and watch. Here's another example. I said you would set this one up from the word problem. You'd have to know how to write cobalt-2 chloride. Chloride's a -1, cobalt's a +2, so you need 2 chlorides with the cobalt. And sodium hydroxide is easy to do, right? Hydroxide is a polyatomic with a -1 charge. Sodium's a +1 charge because it's an alkali metal. And you write those correctly, then you balance the equation. It required a coefficient of 2 for sodium hydroxide and 2 for sodium chloride in order to balance the equation. Once the equation is balanced, then you can break it apart. And notice when you break it apart, the subscripts become coefficients in this case. See, cobalt chloride breaks apart into cobalt-2 plus ion and 2 chloride ions. Okay. And then you just cancel the spectators. The ones that are the same on both sides, didn't change. Those are spectators, and you're left with a net ionic. All right. Can I afford to do this? Let's see what I got on the agenda. Yeah. We can finish this lecture on Tuesday and then do the review on Thursday. So this will give you enough to chew on, right? I've only got 5 more minutes, correct?
Yeah.
Okay. I think that's why I put this slide in there so that I know when to pause. This is a good place to pause because after this, we get into the stoichiometry of solutions, right? And you can look ahead if you want. There's no law against that. But this is as far as we're going today because we only have an hour and 15 minutes, right? Hour and 50. Yeah, hour and 50. Yeah. So we're gonna put the brakes on right now and pick it up on Tuesday, finish this lecture, and then we'll go in the lab and do our lab techniques. So you will need a lab coat. I have eye protection, or you can get your own if you want. Mine probably got scratches on them. And you want to dress appropriately, right? Anything below your lab coat has to be covered, right? And no open-toed shoes.